So we can dive right in. So the first question here, it's on the screen, has to do with mirrors. It says, in the diagram shown, we have a 2.5 meter tall object. It's located on this coordinate axis at x equals 0.5 meters. It's in front of a divergent lens. So that's kind of indicated by this little symbol here on the ends. If this was actually drawn out, it would look something like, be a lot thinner, I guess, but something like this. Not to be confused with a converging lens or a convex lens, which would be something like that. So we have the one on the right. So the focal length of this is minus 2 meters. The minus sign also tells us that we have a diverging lens. If it was a positive focal length, we would have a converging lens. This is all kind of just consistent. We're asked to draw all the principal rays, the focal points, and figure out where the image is and how big it is. Then we're going to use the thin lens. Oh my gosh, there's so many typos in this. Thin lens equation. Calculate the exact same things that we get from the drawings. This is kind of similar to the mirror question from last week. Basically use graphical methods to figure out where the image is located and then confirm it using equations. So let's start with drawing our, actually no, let's start with drawing our focal points. So they're 2 meters. With lenses, you can draw one on either side. Kind of the primary one that we're going to be using is on the right side. But there's an identical one on the other side. We get one on either side because, of course, the lens is transparent. With a mirror, we kind of only draw one because it's not transparent. Anyway, so moving on to the principal rays. I guess we could switch away from blue because we just use that. It doesn't really matter what order you progress in. Most of them are going to be similar to the ones we did for a mirror last week. I'm going to start with one that is parallel to the optical axis. All of these, remember, they have to pass through the top of the image and then follow the constraint that we set out. So in this case, the constraint is that this is parallel to the optical axis. And one thing to keep in mind, these ones are particularly tricky in my opinion, the diverging lenses. So what you expect is if you have a lens like this, I'll just draw like a kind of rough approximation. If you have light rays that come in, obviously they can come in at various angles, but they spread out. They diverge. This is kind of what it means to be a divergent lens. So what we expect is this green ray that I've drawn coming in from the left. What it should do is it's going to bend kind of upward towards the top right hand corner of the page. The way we figure out what the actual angle that it goes at is it's going to, kind of the rule is when you have an array that's traveling parallel to the optical axis, hits the lens, it's going to bend and pass through the focal point. So what we actually want to do is consider this focal point on the left here. So what I'm going to do is I'll draw something like this. So if we put some arrowheads on this to kind of make it clear what's happening, this is coming in from the right and going out like this. And what we've done here is we've kind of just traced back a virtual ray. So this bit of green that I put the dashed over, it's not a real ray. The light actually doesn't pass through this area. It kind of goes up into the right, like I said it would. But if we have a virtual image, we're going to need to consider this drawn back image. And it's a bit of a spoiler, but I think we will have a virtual image. So that's our first ray. One that we can do next is from the top of the object again through where the lens meets the optical axis. When that happens, the ray passes through, no change in angle, unrefracted, that kind of thing. So again, we can put some labels on this just to make it clear what's happening. So this one passes through exactly as I said. And to be honest, we can figure out exactly where the image is and how big it is and that kind of thing from two rays only. You can see where this virtual one that we drew back and this one over here where they intersect. So we do kind of have the ability to conclude at this point that the image is going to be here. But suppose that you made an error with one of these, it's always best to do more principal rays just to make sure they all agree. So we'll put finally a pink one in. What I'm going to do now, we did the kind of parallel to the optical axis, refracting through the focal point. We'll do the opposite one, which is comes in, imagine that it was parallel, or sorry, not parallel, passes through this focal point. I'm just going to draw this to here more or less. Notice this is what we expect this to do is going to come along here and do this. This is what the real ray does. We have to trace back. I didn't do a fabulous job of lining those up, but let's label this to make sense of it. So the pink one, it's passing into the focal point. I chose the right focal point because remember this has a negative sign in front of the focal length. This is a diverging lens, so something that comes in like this should do that. So the arrowheads kind of denote what the real ray does, but then the virtual ray that we might want to trace back, I've put dashes over. So this does agree nicely. We could even put a proper arrow. It's not very good. Something like that. Exactly where all three of those converge. And so all three of them converge in the same place now. So the uncertainty that I said we had with only two rays is kind of removed. All three of them agree. Yeah, so I think now we're set to kind of move on to the second part of this and try and figure out if what we get from the thin lens equation agrees with what we got graphically here. So with that in mind, let's maybe label some of the distances we're going to use. This is the image position. Usually we call this S prime. Or the image distance. It's the distance from the image to the optical element. Same thing for the object, that's just S. And the thing to keep in mind, and we had this last week with the problem on mirrors, is positions are being referenced to this x-axis, this number line here on the bottom, but the optical element is not positioned at 0. So if you have the object at 0.5 meters and the lens is at 5 meters, that's 4.5 meters for S, something like this. So for all the numbers we want to put into the thin lens equation, we need to reference them, their distances with respect to the optical element. We also have the heights that we might be concerned with, so the object height h and the image height h. We already have the focal points labeled. So the thin lens equation says that the reciprocal of the focal length is equal to the sum of the reciprocals of the image and object distance. So we know what S and F are, but let's solve for S prime perhaps. So 1 over S prime is equal to 1 over F minus 1 over S. If we cross multiply, we'll get S minus F over SF. I forgot my prime there. And we can then flip the fractions on both sides of this to get an equation for S prime. So all of this should look identical to what we did last week with mirrors, because the physics behind this equation, this is the thin lens equation. We had the equivalent for mirrors last week, but they're really, in terms of the hardware, they're the exact same. So let's solve for S prime with the numbers we have. The object is 4.5 meters from the mirror, like we said. The focal length is minus 2 meters. And then we just take the difference of those two numbers in the denominator of the fraction. So this becomes minus 9 meters divided by 6.5 meters. This is 6.5 because notice we have minus and minus. So the bottom actually is becomes 4.5 plus 2. And this will equal something like minus 1.39 meters. What we can read into the minus sign is a few things. Firstly, it means the image is virtual. And normally with a lens is a transparent element. If you have an object over here, kind of your naive intuition might be that the image should be formed on the other side. That's where all the rays go. That's where all the real trajectories are for the light that passes through. So what we typically do is we measure, this would be S prime greater than 0. If the image is formed on the right-hand side, or in other words, the opposite side of where the object is, if you happen to formulate an image like we have here on the same side of the lens as the object is, then this is considered to be a negative image distance. And this only happens when we have a virtual image, so negative also can mean virtual. So this is okay. This negative sign, we have 1.39. Notice that kind of 1 meter here is where I put this little dot. 1.5 is where I put the second dot. So at about 1.4, I think the drawing is pretty accurate. So the equation and the drawing are kind of, they agree. Let's go through and calculate the height next, just to make sure that also agrees. We didn't just get the position right. So the height of the image divided by the height of the object is equal to the negative of the image distance divided by the object distance. So we want to solve for is h prime. That equals h minus h, excuse me, times s prime divided by s. So we have all these numbers. H is 2.5 meters. We can either get that from the details of the question or the diagram. S prime is what we just calculated, minus 1.39 meters. And S was given in the problem. It's 4.5 meters. So plug this into your calculator. The two negatives will go away, and the height will be 0.77 meters. And the fact that the two negatives went away is good. This plus means that we have an upright image. So that means that the image is in the same orientation, basically, as the object. So the object in our diagram was pointing up. You can see the arrowhead points up. We found that our image is the exact same. It also points up. So this agrees, again, with our diagram, which is fantastic. Lastly, we need to calculate the magnification. A couple different ways we can do this. The one that makes most sense to me is just taking the ratio of the heights. So we have 0.77, which we just calculated. That's the image height. 2.5 was the object height. And we get 0.31. So this number is less than 1, which means the image height is smaller, which again, the arrow that we drew in, it's smaller than the object. So everything is consistent and everything makes sense, which is good. Okay, so maybe we'll box off the answers for anyone who's going to come watch this later. But with that, we will depart from optics and we will move into electrostatics. Obviously, if there are questions that come up and we want to circle back at the end, we can definitely do that. I may have lost. There we go. Hopefully you guys didn't get bothered by that. I just lost the window on my screen for a second. Okay, so moving into electrostatics, specifically a question about the electrostatic force. So we were told that three identical charges denoted with the variable Q, Q being 3.61 microcoulombs, are placed on the vertices of an equilateral triangle of side length A. We're then asked what charge, capital Q, must be placed in the middle of the triangle equidistant from the three charges Q so that the system is in equilibrium. So there's a few ways to go about this, but regardless of which way we want to choose, I need to try and draw an equilateral triangle. which hopefully will not present too much of a challenge. And if I don't get it perfect, hopefully we can all agree that it's equilateral-ish. So I think that's pretty good. So we have a triangle. We'll denote that it has side length A, and every single one of these is going to be 60 degrees. So if my drawing's inaccurate, hopefully the labeling of the angles and sides ensures that everyone believes at least that it is equilateral. So at the corner of these, or at these corners, we have charges. So I'm just going to fill in some circles. They're point charges. They really have no spatial extent, but we'll give them a dot nonetheless. And they each have charge Q. And I'm going to label them as Q1, 2, and 3. The only reason I'm going to do this is to help us label some of the distances that we're going to be working with. But I'll make a note here that we agree that even though these are labels, the value of the charge for all of these is just equal to lowercase q. So Q1, charge on particle 1, Q2, the charge on particle 2, Q3, the charge on particle 3, they all equal Q. That's what we're told in the question. I've just added this labeling to make our lives a little easier. And lastly, some charge Q in the middle, capital Q. We'll try and put it in the center. And it's sort of equidistant, we're told, to all of these other ones. And what you can imagine happening, actually, let's pretend I didn't put Q in. There we go. Let's pretend I did not put Q in yet. We're told that we have to put a charge in for the system to be at equilibrium. So what equilibrium means is that the sum of the forces on each of the particles individually and altogether is equal to 0. So the reason that we don't have this right now, hopefully you guys fully understand this already because of the awesome content in lecture, but if you don't, imagine the perspective of Q1. This is the perspective that we're going to take in solving this because of symmetry. The same thing's going on at Q2 and the same thing's going on at Q3. So right now, these are all positive charges. They have 3.61 positive microcoulombs, right? So that's they have a deficiency of electrons, which leaves them with a net positive charge. So charges that are of the same sign, they repel each other, and the direction that that repulsion acts along is the distance or the kind of the vector between the position vector between the two charges. So there is a force here. We'll call that, let's just call that maybe F13, the force on charge 1 due to 3. And there's also F12, the force on charge 1 due to charge 2. So there's some sort of net force that's driving Q1 this way in the current model. If we add in the required charge capital Q in the middle, we would hope that we can figure out what its charge has to be on this position so that we can get it to cause a force on Q1. Maybe we'll call this F of F on 1 due to Q, capital Q. And at that point, the net force would be 0 on Q1. And the same story would be true for Q2 and Q3, just kind of by symmetry. So we need to figure out what the size of Q needs to be to kind of cancel out what's happening at charge 1 due to charge 2 and charge 3. So hopefully that's clear. I might tidy this up just to give us as much space as possible. Maybe get rid of this angle too, because I think we're going to need to draw kind of all over this. Okay, so I think we're set. So what does this really mean? We'll take this from the perspective of Q1. This is our charge of interest, but we want to solve the sum of the forces on charge 1. Those are vectors, and this is kind of I think the reason why most students find this unit to be challenging, or maybe not even challenging, just a lot of work. It's because everything is a vector and the directions are very important, right? So we have to, in most cases, or until we get a few more topics in, we have to keep track of all the directions, all the unit vectors, all that kind of stuff. So the sum of the forces on one, we'll say that's equal to the force on one due to two, the force on one due to three, and the force on one due to q. These all have to add up and sum to zero. So all the x components have to add to zero, all the y components have to add to zero. So these are just point charges. So from Coulomb's law, we know what the kind of the force looks like. So the force due to Coulomb's law is equal to 1 over 4 pi epsilon naught. Yeah, so John just asked if F12 is equal to, yeah, exactly. Kind of the argument I made a second ago saying the story is the same at Q2. That's exactly it. I was going to draw what was going on at Q2. Kind of F12 would be this way, and, or sorry, labeling F21 and F23 will be pointing down this way. So yeah, exactly the same. That's basically Newton's third law, right? While I have you guys, and there's actually a little activity in the chat, can you guys confirm for me? Do you guys use this in front of forces and fields, or do you guys use kind of the constant K? I think Professor DeVette uses 1 over 4 pi epsilon naught, but some profs are different. Okay, cool. Yeah. The fraction is a little more meaningful, so it's good that it's more helpful for kind of future topics. So 4 pi epsilon naught, we'll just call this qi, qj, it's just for generic like labeling 1, 2, 3, whatever that may be. We have the distance between the two of them that gets squared, and then we have the force acting along the unit vector between those two. So this is a constant, this bit out front. The charges are super simple, especially in this case. Like, what's wrong? There's nothing scary or hard about 3.61 microcoulombs. The challenge is finding the distances, these r's without a vector sign that get squared, and the unit vectors. So what I find is the best way to go about this is to take a painstakingly slow and detailed approach to it. You just keep track of everything along the way, and there's no way to go wrong. So what we're going to do is we're going to we're going to write down what is the vector between R1 and R2. And to make this perfectly clear and to make this representative of what the physics is actually doing, we know that the force is going to point this way. So this is what we're going to call the vector R12. Starts at R2, or sorry, starts at Q2, ends up at Q1. And the other thing that I'm going to do to make this convenient is we're going to say that where Q1 is 0, 0. That's our origin. Nowhere in this question were we told that we have to put this at x equals 5 or anything like that. So to make our lives easier, I'm going to call this 0, 0. And remember that the length of this triangle is side length A. So to show you what I mean and to actually start writing some numbers down, the vector between R1 and 2, its length is A, and it points to the left horizontally. So it's just that, minus A in the I hat direction. So to try and keep this organized, I'm going to switch colors frequently. The next thing we're going to figure out is what is the length of this vector. So R12 is just the length because there's only one coordinate. It's very straightforward. It's just A. And lastly, if we take our vector and we divide it by its length, we get the unit vector. So this is just equal to minus I hat. And this is a good place to start because I don't think you need to do any calculations to figure these out. The next one's perhaps not so easy. So let's do it. What's probably the next simplest one is R13. Just a reminder that this one's going to point from R3 all the way down to R1. So we need to break out a little bit of trig. We can kind of divide this triangle in half because it's equilateral. This is really this x coordinate here. It's a over 2. That's easy. And we know that this angle is 60. The cosine of 60 is a half. We get the vertical component from sine of 60. And I think it's quite clear that the length of this is a. So a over 2 in the I hat direction minus root 3 a over 2 in the j hat direction. And I was trying to keep things in nice columns, and I've already kind of encroached on the next one, so maybe I'll make this a little smaller. So if you're wondering where these came from, I kind of just mentioned it, but this is sine of 60 is where I get the 1/2 from, and, or sorry, cosine of 60. And if this is confusing to you, just kind of reconstruct the triangle that I made here. Because this vector goes along the edge of the triangle, hopefully it's clear that the length is also a. If you didn't believe me, you could also take these two components in the vector and square them together. And the corresponding unit vector we get from dividing these is just minus a half I hat minus root 3 over 2 j hat. And again, this comes from the sine of and cosine of 60. Two of the kind of the easier ones, if you ask me. This one here, Q, we need to work a little bit harder. I'm going to, again, make a bit of space so that we can draw a simplified diagram without getting anything too messy. Okay, so let's put back in the charge I just erased. And then maybe we'll do it in red. So this is the vector that we're trying to draw. This is we're calling this R1Q. And the triangle that we want to work with to kind of figure out what the X and Y coordinates are is this one here that I've put out in red. So there's a few things that we can leverage and make this pretty simple. Because my drawing is not fantastic, but because we know that Q has to be at the center of this triangle, this is a 30-degree angle. We also know that this is aligned with the center of the triangle here, so this is A over 2, which is kind of a result we used previously. So redrawing this with a bit more space, if this is A over 2, if this is 30, then the vertical coordinate here that we're looking for is, I believe this is A over 2 tangent of 30. Let's just verify this. Opposite side, which I'm calling y for now, divided by adjacent side, that's tangent. Yeah, exactly. Okay, so I'm convinced that that's A over 2 tan 30. The only thing we need now is what the heck is tan 30? We don't necessarily need a calculator. Tan is just sine 30 divided by cos 30. Sine of 30 is equal to a half. Cosine of 30 is equal to root 3 over 2. So I think that should leave us with 1 over root 3, which is helpful for someone who doesn't have a calculator. Yeah, tan 30 is 1 over root 3. So this is A over 2 root 3. Okay, so I think we can copy this over to our kind of our note area here on the left. So we have R1Q. This is going down to the left. So we have minus A over 2 in the I hat direction minus A over 2 root 3 in the J hat direction. Okay, so let's tidy this up a bit before we finish the rest. And you guys can see what I was talking about, right? This is almost painstakingly slow, right? But this is what we have to do. We have to work and get all of these coordinates out so that we can actually just put them in. And then the physics is actually the simple part. It's the geometry and the vectors that are challenging. Okay, so we need to figure out what the heck the length of R1Q is. I could give you an answer and you guys could believe me, but it's pretty straightforward to figure out for ourselves. So again, we'll do it off to the side here. We'll just take each of these coordinates and square them. So we have a squared over 4 is our first coordinate. We have a squared over 4 times 3. That's our second one. So we have 1/4 plus 1/12. Oops, 3/12 plus 1/12. This seems slightly wrong to me. No, it doesn't. We have 4/12. So that's root 3. Root 3a is our length. Okay. And lastly, we need to write down what the unit vector is here. So dividing by root 3a is actually pretty straightforward. We have minus 1/2 root 3 in the I hat direction minus. Someone pointed out this is supposed to be a over root 3, right? I just heard the chat notification. I bet that's the correction. Okay. You guys did not get the correction, so we'll fix that in a second. John was asking, did I miss why R1Q has negative coefficients? Yeah, so the way that I denoted this, we're figuring out all forces on charge 1, and we're assuming through the symmetry of the problem that this applies at 2 and at 3 and that kind of stuff. So we can figure out what it takes to make all the forces at acting on charge 1, 0, then we're good. So yeah, all the vectors are pointing the force from 3 on charge 1. The vector starts at 3, points at charge 1. 2 on 1 is the same, starts at charge 2, points at charge 1. I've actually still left it there in the drawing, right? So that points to the left, and same thing with R1Q, it's down to the left. It's kind of like, where's the origin of the force? Where is it acting? That's kind of your before and after if you're trying to, or your tail and your tip of your vector. Okay, so I made a boo-boo here that I denoted. This is A over 3. So let's change back to blue. And if you put root 3 into your calculator, that's a number greater than 1. So that would have meant that this distance is longer than the side length of this equilateral triangle, which makes no sense. So good thing we caught that. Okay, so let's correct these. So A over 2 divided by A over root 3. Oh, wrong color. Is root 3 over 2 I hat minus 1/2 j hat. And you might say these look pretty familiar. We just found them from what is the vector and what is the length of the vector, and using the definition of the unit vector to figure that out. But you could also realize that this is the cosine of 30 and this is the sine of 30. So it's all kind of consistent. And finally, after all that long and painful kind of vector stuff, we are finally at the point where we start plugging real numbers in and writing out these forces. Okay, so let's switch back maybe to blue. And we're ready. So what we're going to do is we're going to write down each of these forces. I'm going to skip this step. I'm not going to write down 1/4 pi epsilon naught Q1, Q2 divided by R12 times unit vector of R1, 2, that kind of thing. I'm going to just start filling in the numbers just to save us some time and some space. So we have a factor of 1 over 4 pi epsilon naught that's common to every single one of these forces. So let's write that out front, factor it out, and ignore it from now on. So force F1 onto 2, we have a Q squared. We would write Q1 times Q2, but remember up here we agreed that they're all equal. The 1, 2, that's just my labeling. They're all equal to Q. The length of the vector between them, that's R1, 2, it's A. We can't forget to square that. Next, we need to multiply by the unit vector, which was minus I hat. So this is, you can see already, this is where things get super simple, right? I grabbed A from here, I grabbed the unit vector from here, and now we're just writing stuff in. Now that we have this kind of nicely organized, we're in a good place. We're going to write down now F13. So Q1 and Q3, they both have magnitude of charge Q. They're both positive. They're both identical, so we just write Q squared. The distance is A squared. So again, this time we have a slightly more complicated unit vector, minus a half I hat, minus root 3 over 2 J hat. But that's that. Still, again, straightforward because we have everything solved previously for the distances and the vectors. Next is the one that we need to make sure we don't just autopilot and write down lowercase q squared again. We have QQ, lowercase q, capital Q. The distance this time we found was A over root 3, so if we square that, it's 3 over A squared, because that's in the denominator of the fraction. And the unit vector have is root 3 over 2 I hat minus half J hat. So it's a bit of a mess, to be completely honest, but it's not bad. So we have an x coordinate and a y coordinate, but we really only have one kind of unknown in this entire equation. So this is the only thing that we have unknown. So what we do, or we could do, is we can gather all the I hat components. Oh, I forgot this has to equal 0. So if we gather all the I hat components, what we'd be doing is saying that we know x and y are independent. We have to sum the forces in x, and those has to be equal to 0. And we'll get this term, we'll get this term, and we'd get kind of this term. And we'd find a value of q, dot q equals. Now, if we did the same thing with the y's, this time we grab anything that has a j hat attached to it. We do the same thing. We get q equals something, and these would be the same. If they weren't the same, we screwed up somewhere. For the sake of setting this up to where you guys can solve it, I'm just going to do one of them, and I'll leave the other one to you guys to make sure that it works out. But we're going to do the one that has the fewer terms, because that seems like it makes sense to me. So we're going to pick the y's. So, because there's only 2 terms there, so basically what we're saying is the sum of the forces in the y direction, just the y components, those also have to equal 0. We have 1 over 4 pi epsilon naught. Actually, well, I'll write it for one line. But if the left side is equal to 0, we can just multiply that away. And what we're left with is, let's get everything with a j hat. So we have minus q squared over a squared root 3 over 2. I forgot my squared. And we had minus 3 q over a squared. And we had a half. This all equals 0, and we have a lot of junk that we can cross off because the left side is 0 and a lot of common terms in both of these. So we have a squareds that go away, we have 2's that go away, we have one of these q's that goes away. What we're left with is 0 being equal to minus root 3 lowercase q minus 3q, capital Q. So in other words, capital Q is equal to minus 1 over root 3 lowercase q. Final answer. Don't know what that is in terms of real numbers. If you put in 3.61 microcoulombs, but that's the result of all the hard work we just did. And the key point from this is that it's smaller. 1 over root 3 is a number less than 1, so it's smaller than little q. The reason it gets to be smaller is because it's closer to charge 1. Remember that this term in the bottom here says that the closer you get between two charges, the bigger the force is. So because capital Q is closer, it doesn't have to be as large in terms of charge to cancel out what's going on due to the charge 2 and charge 3. The other thing it says is you need it to be negative. This makes sense because a negative and a positive force will have an attraction that's going to counteract the repulsion from charge 2 and charge 3. So it's all by design, it all works out, and it's all consistent, but it thankfully makes sense. But you can see, I think this is a really good kind of illustrative example of how there's nothing really that challenging about these. It's just a bit of geometry, but it's a lot of work, and I think it gets perceived as very hard because some people don't set out to keep track of everything. We kind of had, if you look at it here, we had these columns. We figured out all the distances before we set out, and we just, by this point, below this line, just kind of plug in and keep the algebra straight. So yeah, so John asked, so you sum all the individual, yeah. So we know that motion in the x direction shouldn't affect motion in the y direction, that kind of stuff. The three components in this case they're all independent. There might be cases where they're not independent, but I don't know if you've ever encountered them in this course. But yeah, so it's kind of like, think all the way back to when you guys did projectile motion in first semester. You could consider the acceleration due to gravity in the y direction independently from anything going on in the x direction. And you can even think of this as like a number, like the I hat there. Imagine that instead of breaking this up like I did, you factored it out, you combined every term that had an I hat. The I hat can't equal 0, so all the terms that are factored along with the I hat to get this thing to come out to 0, they have to equal 0. It's kind of another argument, but a reframing, I guess, of it. So yeah, so I guess for John specifically, or anybody else who's interested, if you wanted to do this, I said sum the forces in y, set them equal to 0, or grab all your y terms from this line here in blue. Do the same thing with the terms that have I hats, the terms in x, set that equal to 0, and find out what you get for q. Hopefully it's the same, otherwise I've made a mistake. Okay, so this is, oh my gosh, we have 2 more and we're getting on in time. So these are a little bit more simple. Hopefully they're less drawn out, but they still follow all the same principles. This is another one on the electrostatic forces. So I have identical point charges. There's 3 of them. They're at coordinates 0, y. So what this really means is this one here that's kind of positioned on the y-axis. We're not told how far up the y-axis it is. The next one is at position x, comma 0. So that's at this point. We know it's at 0, but we don't know how far along the x-axis it is. And then this one here that has a force vector attached to it. That's obviously kind of, these make a rectangle, right? It's at position x, y. So what we're told is an electrostatic force is exerted on charge at x, y. And we're given what that vector looks like. It has some sort of magnitude, and particularly it has an angle. It makes an angle with respect to the horizontal. We're given y here, and told that the angle that this force makes, it's 50. We have to figure out what x is. This one is deceptively simple, I think. You guys should know, right, from lecture that if you have a point charge, that the force points radially, right? Or the electric field points radially is another way to think about it. But if you had a charge here, kind of like this guy and this guy are separated, then the resulting force vector is going to point like this. In other words, if we say that this force capital F has a y component, the entirety of the y component is due to the interaction with this charge right here. Similarly, you could imagine, ignore these two that I drew. Imagine you had a charge over here, kind of like these guys are oriented, and the resulting force on the one on the right due to the one on the left points to the right. So in other words, if there's some x component felt at the force that's at position xy, it's due entirely to the interaction with this one on the left here. So I said this one's pretty simple, probably good for me to show you guys why. So if we have this for f and there's an angle theta, given what I've drawn for fx and fy, I think you would agree that tangent of this angle theta is equal to fy divided by fx. So these are just components, they're scalar quantities, no vector signs attached to fy and fx. Fy and fx are really just the sides of a triangle that's kind of carved out by f and theta. So what are Fy and Fx? Fy and Fx are just, they come about from Coulomb's law due to the interaction of this here with the two particles we've been talking about. So let's kind of clean this diagram up a tiny bit and maybe shift these X and Y labels to somewhere more meaningful. Okay, so let's do Fy first. That's the force in the Y direction. It's due to the separation here between these two charges, and this distance is y. So that means that Fy is equal to 1 over 4 pi epsilon naught. The two charges are q's, so we're just going to have q squared. The distance we just wrote in was y. It's y squared, and we already previously agreed with the discussion kind of 10 seconds ago that this points in the vertical direction. And I've already called it F1, we're just looking for the components. This is not a vector, this is just the component, kind of the scalar value without a direction. We can do the same thing for this charge on that's pinned to the y-axis. The distance here is actually x to the charge of interior. So we'll go through the exact same process. It's just 1 over 4 pi epsilon naught. The two charges are again q, so we square it, and we are left with a distance of x squared. A lot of this stuff goes away, and what we're left with is that tan theta is equal to x squared over y squared. Or in other words, we're looking for, what are we looking for? We're looking for x. So x is equal to y times the square root of tangent of 50, not 30. So I think in the interest of time, I won't whip the calculator out and figure out what that is. I'll just leave that for you guys, and we will move on to this one, which I think is a little more complicated, but not too bad, and hopefully we get it done in the allotted time or not too much extra time. So similar construction to problem 2, but this time we have a square, which will hopefully be a little bit nicer. We have 4 charges placed in the corners as shown, but they have different values this time. We have Q1, 2, 3, and 4. The side length of the square is L, and that ends up being 2 centimeters. I think I'm going to leave the actual values for you guys. We'll just find an answer in variables. You guys can do the calculator work if you want. So charges are integer values, which will probably make the computation a little nicer, but still the fact that they're different means that they won't kind of, like here, this got really simple because we got the cross out. The fact that the charges were all the same, the q's just went away. It was really nice. We won't be able to do that in this question, but what we're getting at is we want to find what the electric field is at the center of the square. So this is electric field, not electric force or electrostatic force. So the difference, the electric force and the electric field are basically, they're nearly the same. The electric field is basically a quantity that we can consider in the absence of a force. So what the electric field at the center of the square is like is kind of the same thing as if you put a positive test charge in the middle, what force would it feel? So it's just kind of like, what does the force look like in the absence of the charge, or what does the, almost like how much push is there if you wanted to put a charge in? That's maybe a bad way to think about it, but hopefully, even with that bad explanation, you guys have a sense of what we need to do. The difference of vector E for this one looks pretty similar. We still have the 1 over 4 pi epsilon naught, just a constant. We have the electric field due to some sort of ith particle. It's due to the amount of charge that particle has times the distance, or divided by the distance squared. So this is the distance between the charged particle and the area we want to consider. In this problem, it's the center of this square. And we also have that nagging unit vector. So this is a vector quantity. We still have to basically proceed in the exact same way. We have to find what all these are hats, all that kind of stuff. To figure out what those are, it's kind of inescapable for at least part. The only simplification is that we don't really have a second charge that we need to consider. So the gist of what this is saying is we want to figure out kind of at the center, let's just, I don't know, center. This is equal to contributions from charge 1, 2, 3, and 4. We could even label in the middle here. This is kind of our point of interest. It's not a charge, so I'm not going to leave it a Q type of label, that kind of thing. And what we want to do, let's label on this so we can visualize it, is this is what I'm just going to call R1. It points charge number 1 to the point of interest. Same thing for R2, same thing for R3, same thing for R4. And I think because it avoids us having to work with, well, I mean, actually I think the negative numbers are inescapable. I think the two most clever choices, I'm going to define Q4 to be the origin. The other thing you could do is you could define the center of this square to be the origin. It doesn't really matter. You'll arrive at the same answer. It just depends on what's easier to visualize in your head when you're figuring out these vectors. Okay, so this one should go a little bit more straightforward. Triangles are easier than, or harder than squares, in my opinion. So let's follow the same color scheme we did before. Let's write down all of our vectors, lengths, and unit vectors. So R1 is equal to L over 2, and all of the coordinates are going to have an L over 2 in them, so I might simplify it right away. This is L over 2 to the right and down. And I think we can just go through all of them like this and move on to the next column. So R2, charge number 2 is up in the upper right corner. To get to the center, we move by L over 2. We need to go left, which is negative I hat, and down, which is minus J hat. R3, our kind of the path we need to go is up and to the left. To the left is minus, up is positive. And lastly, L over 2, I hat plus J hat. So I think that should be pretty straightforward. Let me know if it's not. The really nice thing about this is we get to label all of our lengths as the same thing, because I think it's pretty obvious, right, that these are the exact same length, they're just in different directions. So the symmetry of this problem helps us out, saves us a bunch of time. So this is going to be L over 2 this way, L over 2 this way. If you can't eyeball it, we can always square the components, add them together. Square root L squared over 2, or L over root 2. But I wouldn't be surprised if a lot of you guys can just kind of eyeball that, or realize that this is a 45 angle and go from there. Okay, so this is, all of these are L over root 2. And lastly, we want our unit vectors. And I think our unit vectors, the way I've drawn this already, is pretty obvious. We just want, I've already written this kind of in magnitude and direction form, so we're just kind of peeling back. Most of this, did I screw that up? Yeah, I did. There we go. I hat minus j hat. R2, or R2 hat, excuse me. Minus, minus, and again, we're kind of trapped in this, not endless, but this cycle of tedious vector work and note taking and that kind of stuff, but it will pay off. And we can just look at what we've compiled and put that right into the equation for electric field and no longer think about vectors. Basically, you have to think really hard about vectors. And if you do that initially, then you don't have to think about vectors anymore to finish out the problem. Okay. Okay, this looks good to me, I believe. Yep, looks solid. Okay, so let's just figure out what the electric field is, and hopefully we don't need to take too much extra space because I don't think I have a spare sheet. So like we did before, we agree there's all going to be a 1 over 4 pi epsilon naught. I'm going to write that out here. Maybe I'll do something even crazier. We agree that this r squared, this length between the charge and the point of interest, that distance, that squared, because we have the same distance for all of them, that's going to be common. So I'm going to factor that out from the first step as well. That's going to be the charge divided by the square of L over root 2. The square over L over root 2 becomes 2 over L squared. So now we can actually write the rest of this stuff in there. So we kind of dealt with this bit, we've dealt with this bit. We have basically what we have left is the charge times the unit vector. So Q1 times 1 over root 2, I hat minus j hat, plus Q2, 1 over root 2, minus I hat minus j hat, Q3 minus I hat plus j hat, and let me make some space. Q4 I hat plus j hat, and I think I forgot my 1 over root 2. So actually, I probably, if I was being really clever, I would have realized that there's a 1 over root 2 in all these terms as well. And they can be figured out. So let's factor these out as we go to the next line. These guys right here. So this equals 1 over 4 pi epsilon naught. We factor out all those root 2's. We're left with root 2 over L squared. And now I'm going to do something. Yeah, let's wrap this all up in one line. So what we want to do, this question says provide your answer as a vector. So the way that we know how to provide answers as vectors is we have a number that's spit out of our calculator times the I hat unit vector. So that's the x coordinate, right? Compute some stuff, get the x coordinate, attach it to the I hat. Do the same thing, figure out what the y coordinate is, attach it to the j hat. So what that really means is if we could factor all of the terms of the I hats together, all the terms of j hat together, we'd be ready. So let's do that. I've already gotten rid of these guys. So basically what we want is we want Q1, that's positive. The other positive is Q4 minus Q2 minus Q3. So if you don't know where these pluses and minuses are coming from, let me first put the I hat here. And basically what I've done is I've factored together all the terms that have an I hat. So notice the Q1 is multiplied by positive I hat, Q2 is multiplied by negative I hat, Q3 is multiplied by negative I hat, 4 is multiplied by positive I hat. So that matches the fact that Q1 has a plus, Q4 has a plus, Q2 has a minus, Q3 has a minus, and they're all multiplied by I hat. We'll do the same thing for the J hats. And the two positive ones we have are Q3 and Q4 minus Q1 and Q2. And those are all times the J hat. So I just did the same thing. And let's switch to red to drive home the point. This is our final answer. It's kind of gnarly, kind of gross, but that's our final answer in variables. If we wanted to compute a numeric value using a calculator or something like that, what you would do is you would take 1 over 4 pi epsilon naught, you would multiply it by root 2, you would divide it by the square root of, or sorry, the square of L, which is 2 centimeters. You'd want to convert that to meters, of course. Then to figure out you take that value and maybe you would keep this as some constant. Then you would take that value and multiply it by this simple addition and subtraction of the charges. You could imagine, we could probably even do this in our heads right now. Q1 is 5, Q2 is 4, that's not, or Q4 is 3, so that's 8. And Q2 is 4, so the difference here is 2. So imagine you got a number out of the front, you multiply that by 2, that's attached to the I hat, that's your X component. You do the same thing with the Y components as well. It's kind of complex, it's kind of gross. This is what you get when you have these vectors and stuff, but it's not too bad, right? Yeah, so John asked a good question, and I think it's actually something that would be good to deal with on a broader scale. Yeah, I think the other thing that's challenging in this unit is that you are being exposed to new metric prefixes attached to some of these units. So I think it's always best to convert to SI, because that means these equations will work and you don't have to keep track of am I in meters, am I in seconds, you know you're in meters and you can forget about it. So things like microcoulombs, obviously want to convert that to coulombs. It makes the number of coulombs really small, but it means you can use the formulas without thinking about it. So 1 microcoulomb is equal to 10 to the minus 6 coulombs. Micro, 10 to the minus 6, you'll get exposed to nano, which is 10 to the minus 9. I don't know if you guys will go into femtometers. Maybe, I don't know. Millimeters, you're used to, obviously this is M as in mm or something like that, or ms for milliseconds, 10 to the minus 3. So you'll have to keep track of that. It's just kind of a new added layer. Converting everything to SI is pretty, I think it's almost necessary. Otherwise, you have to keep track of just so many different units and ask yourself which ones cancel out, which one don't. Yeah, so if you were going to solve what I've provided you guys, and you want to actually get a number out from the calculator, definitely convert to like 5 microcoulombs, definitely 5 times 10 to the minus 6, and so on and so forth. The 2 centimeters, 2 times 10 to the minus 2 meters, that kind of stuff. Because this is usually the problem, is this guy here is in SI units. So, and I don't know how to convert 1 over 4 pi epsilon naught into something that's not SI units. So, yeah. So I think that's all I have for you guys. Thanks for coming at an off time, and obviously the recording's up for anyone who didn't come. And thanks for the good questions. Hopefully you guys don't find this stuff too challenging. I know I mean, I think there is a lot of students do, but hopefully this is helpful and you guys realize that it's just like it's a lot of being careful and keeping track of stuff, not actually challenging concepts that make your mind bend in a weird way or something like that. So yeah, if we have any questions that are lingering, happy to